along. I'm just going to keep going for it here. Let's build up the helium atom. Can we do it? As it turns out, we can't, but I'll talk about why. Okay. So we start by putting the fact together that we have 2 electrons that we're now dealing with. Okay. And the 1 and the 2 right here corresponds to each of those electrons. So we would have electron number 1 that's got some radial dependence, and we've got electron number 2 that also has some radial dependence. And so through our separation of variables, right, we make a product out of those, okay, which means that our Hamiltonian is going to be a sum, okay? It's going to be, right, the operator for electron number 1 plus the operator for electron number 2. And when we apply that total Hamiltonian through this wave function, right, psi of electron 1 and electron 2, this will then commute algebraically, and our energy solution also becomes a sum. All right? And so then, of course, we could plug all that back in and still satisfy our simple Schrodinger equation. So what would that operator look like? Well, we would have for electron number 1, right, we would have a kinetic term. So I'll abbreviate that by saying EK for electron 1. And then, of course, we've got a potential energy term for electron number 2, or excuse me, for electron number 1. Then we also have a kinetic energy term for electron number 2, as well as a potential energy term for electron number 2. Okay, so let's put all of those subtraction signs. So, right, we're seeing kinetic energy and potential energy for electron number 1, kinetic energy and potential energy for electron number 2. But now, what about this other term right here? Well, as it turns out, if we kind of compare this term to our Coulomb's law, right, E squared over 4 pi R12, okay? This describes the electron-electron interaction. And so that's described as a potential energy. Okay? So there's potential energy between the 2 electrons. And you also notice that it has an opposite sign. So I'm going to say plus V12. And the reason why it now has an opposite sign is because, recall, a negative potential describes an attractive interaction, right? So V is less than 0, it's attractive, which makes good sense when we're talking about an electron-proton system. When V is greater than 0, it's repulsive. And that makes sense when we're talking about an electron interaction, right? They're going to repel each other. They're going to want to separate from each other. So that's why it's a potential energy term, because the electrons are forcing each other to separate. Well, as it turns out, just by adding this little extra term right here and then attempting to solve this Schrodinger equation through our normal means, it fails. There's no analytical solution available. And what we mean by analytical solution, there's literally no solution to our differential equation that evolves from putting this whole Schrodinger equation together, okay? Right? Imagine like smashing this whole operator into our Schrodinger equation and then applying the separation of variables. You know, each one of these psi of R1, right, it equals R of R1 times Y of theta 1 phi 1. But if we were to put that whole thing together for both electrons, we would have 2 of these R terms, 2 of these Y terms. We'd throw that operator in there and it would fail. We would not be able to solve this thing. And the biggest reason is because these electrons interact, okay? As it turns out, if we didn't have to have this last term in here, this system would be solvable. However, it wouldn't be very accurate because we know that electrons interact. Okay? So lots of approximations are required. And we're not going to spend a whole lot of time in this class going through those approximations because that's where the entire field of molecular modeling is born. Okay? And when we get into chapter 10, when we start talking about more with molecules, I'll mention a few of these methodologies. If you took molecular modeling, Chem 330 with Josh Smith, you talked about density functional theory. That's one way of approximating these multi-electron atoms and molecules. Hartree-Fock is another method. So there's all kinds of named methods that go into making these approximations. And all of them rely on using a computer to solve the problems for us. Okay?